This chapter is one of those that scares people away from understanding statistics. Read it, but do not panic if it doesn't make a lot of sense. I'm going to go through it conceptually, and the order is going to be a little different than the chapter because I want you to see the big picture and then the reasons for understanding the pieces. Right up front, let me give you the whole purpose for this chapter, and then I'll break it down. I'm going to start with a bit of review. We've been working with using the normal distribution curve. This gives us the probability of a score or a data point. And remember that you can figure out the proportion of scores in a distribution based on table C.1. Remember that the z-score is the number of standard deviations above or below the mean. A z-score of 1 is one standard deviation above the mean. A z-score of negative 0.75 3/4 of a standard deviation below the mean. Looking at table C1, you can see the proportion of z-scores of 0.75 or lower, so below that point, is 22.66%. The proportion of scores above the z-score of negative 0.75 is 77.34% of all of the scores. If I have a score that is a half of a standard deviation above the mean, I look in table C1 for a z-score of 0.5. And I find that the proportion of scores below that z-score is 69.15%. If I have 100 scores, 69.15 of them are below a half of a standard deviation above the mean. If I have 1,000 scores, 691.5 of them are below that 0.5 standard deviation above the mean. Notice that the percent of scores way out in what we call the tails is very, very small. The proportion of scores at 2.75 standard deviations or above, for example, is 0.0030 or 0.3%. If I have 1,000 student scores, 3 of them are likely going to be that high in a normal distribution. Very rare. Now back to this chapter. Instead of thinking about scores, think about the means or averages for a whole bunch of samples instead of test scores. So replace in your mind the idea of test scores or data points with the means or averages of a bunch of samples. Let's say I draw a sample of 100 scores and find that their mean is 55.62 with a standard deviation of 8.10. I have all the time and all the resources in the world, so I'm going to put those 100 scores back into the population and draw a second sample of 100 scores. It is very unlikely that I'm going to draw the second time exactly the same combination of 100 scores. Some of them may be the same as the first 100 scores I drew, but not likely all of them. And that's the beauty of randomly drawing them. My sample has a mean of 4.83 with a standard deviation of 8.64. I'm going to keep doing this because I have all the time and all the resources in the world. I wish. The third time, my sample has a mean of 53.97 and a standard deviation of 8.38. I could keep doing this as often as I wanted, and every time I'm very likely to come up with a slightly different mean and standard deviation. But how likely is it that I'm going to pull a random sample of 100 from this same population with a mean of 28.37 and a standard deviation of 12.82? It is a possibility. I really could pull that combination of scores. but it's incredibly unlikely. In fact, if I pulled 1,000 different random samples, I bet I wouldn't even pull one like that. It's going the probability of pulling that is way, way down low in the tail of the likelihood. If I look at the standard distribution as a likelihood, it's not going to happen very often, is it? The likelihood or probability of pulling the random samples with means in the mid 50s is much, much, much higher. And that, in a nutshell, is the purpose of this chapter. We can use table C.1 to find the proportions and probabilities of different means for samples. Quick review, we use the normal distribution curve and table C.1 so that the math has already been done to describe the distribution of scores in a population or in a sample that represents that population. And we change those scores to t-scores, and then they represent standard deviations from the mean. Now, in this chapter, we find out that we can also have a distribution of the mean for each and every possible random sample, a distribution of the means for those samples. This is the sampling distribution of the mean. Instead of scores, the distribution is all the possible means for that of the samples from that population. We have to change all of those means to z-scores, but they no longer represent standard deviation. They're going to represent standard errors, but you'll find that they work the same way as the standard deviations. And we'll come back to that next and take a look at the difference between standard errors and where we get those from and use them in z-scores, and standard deviations and review where we got those from and how we use them in the distribution. So this is not really new material. We're using an underlying distribution curve, but instead of looking at the distribution of scores, we're looking at the distribution of means from an infinite number of possible samples from that population.